and after linearization we get the linearized model, large signal model. From that we just segregate the DC model and also segregate the AC model. Then this is in state space form. If we need it in a transfer function form, then we take the Laplace transform considering the initial conditions to be 0. Then we get the transfer functions. That's the things we have discussed, right? So now this is already done. There may be multiple modes based upon the number of switches or the CCM or DCM. Then we write these equations, then we do averaging, then we introduce perturbations and linearization. And after linearization, we get these models. We get steady state model or DC model, then we get dynamic model or AC models. Then these models can be used either in this form, or if we need transfer function, then we can get various transfer functions that we have already discussed based upon the input and outputs. So like if you say second order converter like buck converters, then we have this X. We have this X to be IL and VC only. But if we say this is a fourth order converter, so this is for buck converter, X will be IL1, IL2, IL3, and IL4. Not IL4, VC1, VC2. This is for a fourth order converter, buck converter. So depending upon the inductors and capacitors, we define this X variable. And other important variable is the output variable. So output side also depending upon what we consider to be output, we define this Y. So normally output we take sometime obviously we take output which is the capacitor voltage, right? We take as output. Also sometimes inductor current also people consider to be output, right? Depending upon the type of control being used. And other thing is this U, variable U. So variable U, now this variable U is control input or disturbance input. So it can be your obviously input voltage, variation in input voltage, it will be there. Then it will be duty cycle. Also, it can be the change in load current, which is represented by IZ perturbation or I node perturbation. So this is called perturbation in load current. Perturbation in and 15. So it depends upon the variables. So next is Leverage algorithm we have discussed. So as I said that if model is second order and it's ideal only, then resolvent matrix, because in all these transfer functions, SI minus inverse calculation is very important. If this SI minus inverse, we go through this direct formula, which is adjoint of SI minus A upon determinant of this, then it's easy. But if there are non-idealities, if there are the order of the system increases for fourth order, fifth order, sixth order, then this becomes a bit complex, and we may prone to error, and there is no way to find out whether the whatever things we have obtained is correct or not. So in order to solve this, this thing is coming in between. This is and from this icon people are viewing Microsoft PowerPoint. Is it visible to you also?
Which icon?
ये बीच में black सा कुछ आ रहा है ना?
Yes sir. सर ये
अच्छा,
वो वीडियो का आइकन है।
हाँ वीडियो का आइकन है सर वो।
अच्छा इसको ओके, सो साइड भी नहीं हो रहा है ना ये?
No, sir.
इससे क्या कुछ कंटेंट्स जो है वो, इसको अगर मैं वीडियो को ऑफ करता हूँ तो
अभी सर
minimize-
चला गया।
अब नहीं आ रहा।
चला गया, अब
आ
नहीं
गया।
आ रहा है।
अब आ गया, आगे वापस आ गया।
कहाँ
सर
गया?
माउस की मूवमेंट से शायद ये।
अभी आ रहा है, अभी भी आ रहा है शायद।
अब
No,
नहीं,
sir.
अब नहीं है।
नहीं आ रहा अभी।
नहीं, अब नहीं है।
Left right black are present. Left right is okay, that will be there, but let me see again why it is happening.
वो डबल क्लिक।
Screen one, screen two, screen one. Share. Screen one. Slide share. I think it's not visible now. True? It's okay now, I find.
Yes, sir. We can give.
Okay, fine. So we were here at this point, Leverrier algorithm. So in Leverrier algorithm, we have seen that we can find these different matrices using these n steps for an order system. And if these n steps are found out, then we can find these coefficients and n matrices. Now, based upon these n coefficients and n matrices, we can get this resolvent matrix, and we will see how to use this. We will see today practical examples, and most important is that we can verify it using this equation. Okay. So now we have seen the how to do the modeling of buck converter, considering the ideal one. We write switch is on, switch is off, then we write these models, then we do averaging, then we introduce perturbations, then we get DC model, then AC models, then these transfer functions. So this much we have done, that how to drive these transfer functions for ideal case. But I told this not the ideal one. When you are going to other classes also, when you are designing a inductor is consisting of a wire and ferrite core, so there will be losses, right? So these losses we represent using a ESR, equivalent series resistance. Similarly, diode, in diode also we have seen the diode characteristics, that there is some potential drop before it goes into forward conduction mode. After that also there will be some resistance due to these whole pair combinations. So due to all those things, we as I told, that if we want to design a good control, then we should know we should be familiar with the physical system as accurate as possible, and that is possible only if we are able to get the accurate model of converter, right? So we try. Last time someone asked questions, yeah, but we try to incorporate the important things only. The important we try to incorporate the important losses. So one is switch loss, other is this diode loss. So this is kind of ideal diode. Now we have separated its losses, which is RD and VF. Here this is RL and this is RC, ESR of the capacitor. Now apart from all those things, these are the non-ideal things. Now we have considered one current source over here. What is this current source basically? This current source is representing as if there is some, let's say if there is some change in current, IZ variations. So this current source is here put to get transfer function of V output or maybe IL with respect to change in load current. So this V naught upon VZ, this gives you output impedance of the converter. Output impedance of the converter. Okay. So we'll see how to derive these equations. So let's say as whether it's ideal or non-ideal, the process remains same, but equations get changed. So this is when switch is on. So our switch was presented over here. Sorry, diode was presented over here. Now diode is forward bias and switch was presented over here. So now this switch is on. When switch is on, then RSW, this loss will be there, which is represented by RSW. Remaining circuit will be whatever as it is, and this diode will not be there, right? Diode will be off only. So this diode will not be there. Now diode is open. How to write the equation? As standard for any converter universally, we need to write its inductor voltage when mode when in any mode. So mode 1 is when switch is on 0 to dt. So in case of mode 1, let's write the this inductor voltage VL, so which can be written with the help of this VL. So we start from here. This is VG minus IL, RSW and RL both come in series and both are experiencing this current IL. So IL will be together and this RL plus RSW will be there. Now after that minus this entire voltage V naught, that is equal to 0. So this is our first equation, right? This is the very first equation we get. Now the second equation we get for this IC, right? IC is what? C dVc by dt equal to. We apply the KCL at this point, and what we find, this IC is equal to, or you can say this IL, current which is flowing here, IL, this current is sum of these three, IC, I node and IZ. So IC will be IL minus I node minus IZ. These three currents. And the third equation, so this is second equation, let's say, and the third equation will be V output equal to VC plus IC into RC. So this is our, let's say, third equation. Now, we have seen that whenever we are one thing we have missed here, this is minus VL. Okay. Whenever we are writing these state space models, we have to put this state space vectors derivative in left. Then in right, we will have, like, we need to form in this form x dot equal to ax plus bu, right? So what we need to do, we need to take all dot or derivative terms on left side and the terms related to this x on the right side, and u is the input. So we know that in this case, our x is nothing but IL VC. Remember that previously this VC was considered V node because both were same, but in this case V node is not directly, instantaneous V node is not directly equal to VC, right? In steady state it will be, or average value will be same, but instantaneous voltage will not be there. Same will not be there. So I cannot write directly here V node, it will be VC only. Our output will be V node, right? And our U here, in this case, U will be, two things will be there in the U. One will be your input voltage and another will be IZ. So these things we know. We have to formulate these equations, or we have to rearrange these equations in same format. So now if I start with this first equation, I just try to find out this VL EL, which is nothing but L di by dt is equal to, now this is equal to Vg minus IL RL plus RSW minus V naught, right? So here we know that this di by dt, whatever we require, that is okay. IL is also okay, Vg is also okay, but V naught is this output. V naught is the output, and output should not come in this equation, right? Should replace it. We should replace it. So out of these three equations, now IC, if I'm writing IC, so that is C dVc by dt equal to IL. IL is okay for me, minus I naught is V naught upon R minus IZ. In this equation, if I see, then this IL is okay, dVc by dt, this term is okay. Minus V naught by R, that is not okay, because V naught should not be there. And IZ is also okay, because this is the part of load current. IZ is kind of BG here, nature, or the variable is kind of, it will be considered in category of VG now. So we have this third term V naught. What we can do, we just put this V naught, we just put this V naught over here, right? And with the help of this V naught, equal to VC plus IC into RC. So that is IL minus V naught upon R minus IZ into RC. Right? So from here we take, and also in this third equation, V naught equal to VC plus IC RC. VC is okay, but IC is not kind of a state variable. So we need to solve for this IC. Right? So if we take V naught to be here, this side, then this is 1 plus RC upon R, right? So that is equal to VC plus ILRC minus IZRC. Okay. Now V naught equal to, from here comes out to be, this is R upon R plus RC. This term will go on right side and will get multiplied to each of the terms. Now let us arrange it in the same fashion. So it will be multiplied with RC into IL plus R upon R plus RC into VC. Similarly, it will be multiplied by this term also into IZ. So this is our V node. Now we see that when we derive this V node, IL we need in right hand side, VC we need in right hand side, IZ we need in right hand side. So we can just express it in state space form. So now we have solved with equation number 3. Now we go back and try to solve this equation number 1, let's say. If you put this value of V naught in that equation, so not this, sorry, we can take help. Let's say this is A, B, C. So this is 1B. No, this is 2A, 2B, 3A. This is 1B. This is 2B. We put, and this is a, let's say 3C, right? So we put 3C into 2, not 2, 1B. Put it back here, then this VL, which is L di by dt, that is equal to Vg minus IL RSW plus RL minus V naught. So minus this V naught. So V naught we will replace with this RC R plus RC IL minus R upon R plus RC VC plus RRC upon R plus RC IZ. We simplify this. So upon simplification, I again arrange it in terms of IL first. So if you take this, then minus IL. So this term will be there, RSW plus RL. Then this term, entire term, plus RC R upon R plus RC into IL. So these two terms, IL terms, has been covered. Now next is the term of VC. So VC has only single term. So this term we will put as it is. This term is covered. This term is covered. Now next is input voltage VG, and the third one is IZ. So this term will be as it is over here. Now this is L di by dt. L di by dt. So if you want to solve this for di by dt, then what we need to do? We need to remove L from here and we divide it. Right? We divide everywhere with L. So here also 1 upon L. Here also 1 upon L. And this term 1 upon L. So this is di by dt. Now we got from equation number 1b this equation. So this is, let's say, your number. Let's number it to be 2 1c. Now we need to get this IC also. So IC equal to dt equal to IL minus V naught upon R minus IZ. So IL minus V naught upon R. V naught is this one divided by R. So this will be RC upon R plus RC IL minus 1 upon R plus RC VC, right? Minus minus plus. So this is plus RC upon R plus RC IZ. So up to we are putting these values in this 2b, right? Value of V naught in 2b minus. Okay, so we are putting this 2b, this equation. So IL minus V naught upon R. So minus V naught upon R, just divide this equation by R. We'll get this term. So this is IZ. So this is IZ. And your original IZ will be there, minus IZ. So just simplify this. So this is C dVc by dt. So what this C dVc by dt is, now we will simplify this term of IL. So R plus RC minus RC. So only thing remains is R upon R plus RC. R upon R plus RC, right? Into IL. Now these two terms are solved. Now VC will be as it is, minus 1 upon R plus RC into VC. Now the third term is this one, plus you see this IZ is 2 times. So if you simplify this, then this will be minus R upon R plus RC IZ. So yeah, right. So if you want to find this dV upon dt only, then what we will do? We will divide every equation by 1 by C. Right? This also 1 by C. So now this is our, let's say, equation to C. So we will arrange all these equations 1C, 2C, 3C in this fashion. So whatever is written over here, this is just these three equations only after simplification. And each equation you can see that we have on the right hand side either the state space variable, state variables, or the input disturbances only, right? So from these equations, we can put it into matrix form and we get these coefficients A1, B1, C1, E1, right? E1. But you must have seen here few more coefficients, J1 and F1, which we had not discussed uh, in the previous one. What is this J1 and F1? Basically, if you see that our standard transfer function is AX plus BU, okay, AX plus BU, and Y equal to CX plus U. Here A is the coefficient matrix for X, B is the coefficient matrix for U. But if there are some constants over there, then how to tackle with that? So in order to incorporate those coefficients, constant coefficients, we have considered the J and F. And you will see when we take into consideration if there is, let's say, like in one of the class, Professor Mishra told that when you model a battery, then you take one voltage source and resistance in voltage source converted itself, we will see the diode is there. Now the diode, voltage source is on. When it is on, then we represent it to be BF, voltage drop to VF. So how to represent that? Because that VF is not function of any U, anything. So how to be represented? For that, this coefficients has been introduced. So our new model we represent in this way. Basically, you can say this J is part of U only if I multiply it with 1. Then I can consider if there is some input 1 corresponding to that input 1, there is a matrix. It is for just mathematical point of view, right? So similarly, we can here also we can write equations. So now in this case, VF is this VF is there. What we do again, we put KVL. So from KVL, we'll get one equation and one KCL we will put here. This is the KVL, then we'll put KCL over here. So with the help of KCL equation will remain same. IL will be equal to IC plus I naught plus IZ. Now the third equation will also remain same. Okay, so third equation will also remain same. That is V naught equal to VC plus ICRC. Now, using the same fundamentals, we calculate the V naught with the help of these two equations. Then we'll put back here that V naught. Then we'll put back here that V naught. We get these three more equations, and these equations are valid when switch is off. So, with the help of these equations, we can form these matrices, which is basically A2, B2, your G2. Similarly, C1, C2, E2. So in these two modes, we have obtained this state space model. Now here there are two modes only. If it is three modes, we could get three A3, B3, J3 like that, right? Now, once we go to these matrices, I have just rewrite these. We can get average matrices using the formulas, A equal to A1D plus A2 1 minus D, B equal to B1D plus B2 1 minus D. Now in this case, because D and 1 minus D are the duty cycles for on and off, But if it is multiple, let's say 3 more, then A will be A1 B1, A2 D2, let's say 4 more, A3 D3 plus A4 D4. Now this D1, D2, D3, D4, they may have relations. D1 may be function, maybe D2 is something 1 minus 2 D1. It is quite possible. Same thing, D3 may be 1 minus D1 minus D2 by 3, maybe some period. So it may be there, right? But in general, we can write it in like that, and that way. So we got from here this individual matrix A, B, E, C, E. Now you will see here that we have got the J matrix also. We got F matrix. F is 0. J is equal to minus D dash. D dash is nothing but 1 minus D. So D dash VF upon L. Earlier it was 0 because VF was not there in ideal converter, but it is there. So J will have to be considered over here. Now we need to get this VD and ED, right? These are the metrics corresponding to duty cycles which are there after the linearization, right? Now these metrics are nothing but A minus A2, B1 minus B2. So we have already A1, A1, A2, B1, B2 with us, J1, J2 with us. But apart from that, we need the DC value of these inputs and a DC value of X. That also we know that we have formula for that. We can calculate X equal to minus A inverse BU with that. Similarly, we can get ED. So now VD and ED is also with us. Today we will learn in MATLAB also that how to use these formulas and get transfer functions for any converter. For any converter, if you know these equations in matrix form, you can get any transfer function for any converter. So these are the basic thing which is required. Now these things are with us. Then we need to get transfer function. Now the model with us will be x dot equal to x dot x equal the x dot equal to ax plus bu. And remember that this J part and F part will not be there in this small signal model. Why? Anyone can tell why? And this y tilde equal to Cx tilde plus. Can anyone tell why this is not there? That we have not considered this B and what we denoted J and F. This J and F is why it is not there. You can put comments in Dropbox also if you are not able to speak. J and F, I have not, this is not present in this X and Y, but this is present when you are calculating, this steady state values. Their impact will be on steady state values only, not on this. Why so? बताइए आप में से कोई. If you simplify this model, then your X will be minus A inverse BU plus J. Earlier when J was 0, then it was minus A inverse BU. And your Y now will be, minus C A inverse B plus E U. So this was the earlier only, right? But now it will be added with plus minus C A inverse. You can derive it as a homework. J plus F. And nothing in multiplication. Can anyone tell why this is happening? Okay, so I tell you why it is happening. why it is happening? That these terms we have used as a constants, right? And when we introduce the perturbation is not introduced in the constants. It is perturbations are introduced in a variable which is varying with the time, right? Which is varying with the time. Let's see some variable x, which is varying with the time. Now we say that this variable of x of t, this variable of time is equal to some its fixed value plus some perturbation in this. This is its fixed value and this is, let's say, changing according to this. But if something is I cannot change. But when I say x takes the value of 5, which may vary 1%, then it is variable, right? So these terms are constants. They will not change. The effect of these constants will come in DC value only when we are determining the value of this x and y, capital X and capital Y, but not on this small perturbation. So this will not be there in transfer function. Now, with the help of these transfer functions, with the help of these equations, we get transfer functions. Their main challenge is this SI minus A inverse. So, we discussed for that Leverel algorithm is that, and how this previously in previous class we have used Leverel algorithm for an ideal converter, and it was quite easy both the way. But if you take the now SI minus A inverse of this A matrix, which is now little complicated. So A matrix is you say A matrix is this one. So this is not same as the simple one. In the simple one, what was the A matrix? If you put all values to be 0 here, all values to be, let's say, 0 here, then what becomes your A matrix? This is Rx. What is Rx? Rx, just I have written D into RSW plus 1 minus D into RD. That I have written to be Rx. So this will be 0 in ideal case. So this is 0. RL is 0, RC is 0. So this term will be 0. So this is 0 only. Here minus 1 upon L, R upon capital R plus RC. So small RC is 0, capital R and capital R. So that is 1. It is minus 1 by L. Here this capital R plus RC, RC is 0. So this is 1 by C. And here also this is minus 1 by RC. So what do you see? This equation was pretty simpler, but this equation is pretty simpler, but not this entire equation, this one, not this equation, right? So if you take inverse of this, then multiply and all, then it may be somewhat complicated. But how do we solve this with the help of Leverel algorithm? So this is a second order system. So two steps will be there. We define Q1 now minus this Q1A. So it is giving you this coefficient. This is your coefficient A1. Now, similarly, we can find Q naught. So this is Q naught, and the trace of Q naught into A, that is this one. So for verification purpose, if you take Q naught into A is known to us, plus A naught into IT, multiply it, it will give you perfect zero matrix. If it is perfect zero matrix, then what we conclude that these parameters which we have obtained for A naught, A1, they are correct only, right? So now once we got this A1 to 1 node, A node, then we can define this Si minus A inverse. So we will not use this method. So let us put it Q1 is where? Q1 is this only into S. So that means this is S0, 0, S plus Q node. So where is Q node? This matrix. So let's say this is Q node 1, node 2, Q node 3, Q node 4. So Q node 1, Q node 2, Q node 3, Q node 4. So this is your this matrix divided by S square plus A1S plus A node. So now you can just add these coefficients, right? So in denominator this will be same, but in numerator what it will be? S plus Q node 1, then Q node 2, Q node 3, S plus Q node 4. So S plus Q node 1. So this is the Q node 1. This is 2. Q0 2, this is Q0 2, Q0 3, as it is we have written Q0 3, and Q0 4. So Q0 4 is S plus Q0 4, S plus Q0 4. So that way we can get this Si minus A inverse. Now we got this Si minus A inverse. If it is there, then we can get any transfer function. So you know that this V0 upon Vg, that is nothing but Si minus A inverse B, 1. Similarly, V0 upon Iz, that is nothing but Si minus A inverse B2. And V0 upon D, C into D, A inverse B plus ED, right? So these values are with you, we put it and we get these transfer functions. So what we can see here that previously we have derived it for ideal. So ideal transfer function was V0 upon D equal to 1 upon LC, Vg upon LC, S square plus 1 upon RC, S plus 1 upon LC. And this V0 upon this was this V0 upon Vg, this was your D upon LC upon S square plus 1 upon RCS plus 1 upon LC. So in all these three transfer functions, what we see that even in all the transfer functions, what we will see the denominator is the same. Why it is same? Because in previous slide we have seen that this term remains same, and this Si minus A inverse is present in every transfer function. It is present in every transfer function. That's why this denominator will remain same. So if you put these non-ideality to be 0, let's see what denominator is. So if Rx is Rd, drd plus 1 minus d into, sorry, Rx is your d into Rsw plus 1 minus d into Rd. Now Rsw is 0, Rd is 0. So this term will be 0. This will be 0. In ideal case, RL will be 0. RC will be 0. That's why this entire term will not be there. Now what it will be? This will be 0. So only term will be 1 upon RC. Similarly, if we go here, this term will not be there. This term will not be there. This term will not be there. So this R will cancel out with R. So only term is 1 upon LC. If we go in numerator of V0 upon T, then what is there? If you see this VF will be 0, this RS, RD that will be 0, so entire term will be 0. In numerator this RC will be 0. Now this is R alone, so this R alone will also be cancelled. Now here what is left? Only Vg upon LC, only Vg upon LC. This side coefficient RC is 0, so only coefficient is 1. So this matches with this. If you go here, in denominator we have already done. The denominator is same. What about the numerator? This RC is gone. This RC is gone. That's why this R will cancel out R. Now this is D upon LC. So what we see that if we have this transfer function which is obtained by incorporating all these losses, then we can get different other cases. In some cases, you can say, okay, you are considering only RL, then you put remaining 0. In some cases, you are saying RL and RC, I want to consider, you put this diode losses and switch losses to be 0. If you want to see the effect of only switch loss, diode loss, then put other losses, inductor losses, current loss, capacitor losses to be 0. So this model once we get, we can do analysis in different way, in all possible ways. Now, other techniques, I will discuss it in brief because we want to go for simulation also today. So, modeling of non-ideal buck converter using average switch modeling. So, in average switch modeling, what we have seen that we have switch and we have diode. We need to represent the switch and diode with its linearized equivalent circuit, right? So, when we are taking this non-ideal switch into consideration, then what we do, we divide it into two parts. So this is S is kind of ideal switch and loss is there, which is connected in series. Similarly, this diode, ideal diode, right? And these two losses, if I say completely, this entire one is kind of total diode. This entire one is the total switch. But for analysis purpose, I am separating it as if there is a ideal switch and resistance is connected in a series. If there is a diode connected with a small voltage source and a small resistance in series, so that way we will, consider the things. Now, when switch is on, this switch is on, this diode will be off. So we are considering this voltage only, voltage across this diode, and current through this diode, that we will consider. Now we will try to obtain here the switch current, switch voltage, diode current, diode voltage. So when switch is on, so what is the voltage across switch? Normally, if I see from these 2 points, because these 2 points makes the switch, then there is some voltage across the switch. But because now for mathematical representation, I am considering RSW to be different from the switch. So now my switch voltage is this one only, right? This one only. Switch voltage will be 0, right? Similarly, here in diode case, during on period, current is 0, and whatever terminal voltage is there, this diode terminal voltage is there, that is Vg minus this RL into ISW. So that is the RL into RSW, that will be there. Similarly, we can find the current through the switch. So in this case, current through the switch is IL, right? Now, what is the voltage across the switch? Voltage across the switch is 0. Now, what about the diode? So diode, we have seen across the diode, there will be some voltage that we have seen. Similarly, when switch is off, so there will be some voltage across the switch. So this is the equation given by, this equation gives us the information about the voltage across the switch. Now in this case, current across the switch is 0. Similarly, we get 4 here. So now we get 4 equations over here. As I said previously, we consider any one to be voltage source, any one to be current source. So just before replacing, we linearize these equations. So for linearization purpose, first we do their averaging. After averaging, we introduce this perturbation and we do linearization, right? After linearization, we obtain these models, neglecting the higher order terms. So now this model gives us the linearized average large signal model of switch. This gives us the linearized averaged large signal model of the switch. So this model is further used to obtain the transfer function. So how it is used? Now we replace this switch with this switch voltage and we replace this diode with this current source, right? So one is dependent current source, one is independent current source. You can say one is a fixed source, one is depending upon the perturbations. Okay. Now remaining things, these parts, the go as it is, because this is the average switch modeling. So we need to do averaging of the switch current, switch voltages, switch diode current, diode voltages only. Now, opening steady state model, what we do, we put all the perturbation terms to be 0. So when all the perturbation terms are put 0, then this is the steady state model which we obtained. And in this model, by applying KVL and KCL, by applying KVL and KCL. So in this loop, if you apply KVL, you'll get this equation, that Vg minus VSW minus RSW into ISW, right? Minus V naught equal to 0. And similarly, you can get this. After solving these equations, you can get this output voltage. But we know that output voltage formula is this one only. For a buck converter, V naught equal to D into Vg. Okay. So it's a not, it's properly audible, visible. Please let me know. Is things properly audible, visible? Okay, fine. So thank you. Now, yeah. So what we see that here, this output voltage V naught, that is not D into Vg. It is something different. In this case, what we will do, no, what we observe that here, this is function of non-idealities. If you put these non-idealities to be 0, then you will get this D into Vg only. Okay. And for analysis of a small signal model using this average switch modeling technique, what we do, as you know, that we put all DC terms to be 0. When all DC terms are put to be 0, then we are left with perturbation terms only. We are left with perturbation terms only. So once we get this small signal model, then what we do? We write again KVL and KCL in this model, and we obtain various equations, basically two equations, right? Now these two equations are, they are function of these state variables, perturbations, input variables, duty cycles, like that. Whenever we are getting transfer functions, then out of these two, these disturbances and control variable, we take only effect of one into consideration. If I am finding the effect of, let's say, I have here IL and VC, then if I am finding the effect of either change in input voltage or change in load current, which I am representing it to be IZ, or change in duty cycle. So these three perturbations are there with me. So I consider only one perturbation at once. Other two perturbations are said to be 0, right? Then I am left with two equations and three variables. Two equations and three variables. So with the help of one equation, I can eliminate one variable. So other equation will have only two variables. So two variables are okay because we want to get a transfer functions, which is just the ratio of two desired variables. So that's how we go forward. So we have simplified this. We got this equation. I could have explained in more detail, but time is not there. So now when we are trying to have this input output to output voltage transfer function, then what we need to do, this is just what we are getting input. Of input voltage on effect of variation in input voltage on variation of output voltage. So we set this duty cycle variation to be 0, we set this IZ to be 0. Now if we set these two things to be 0 in the previous equation, then what we get is this equation. And if you simplify it V naught upon Vg, then obviously this is function of S only, right? It's not written, but this is function of S. So this is the transfer function. Now we put the value of Y naught and ZL, right? And we get this transfer function. So this is the same transfer function which we have obtained using the state space averaging. Now output current to output voltage transfer function. So when we are getting this output voltage to output current transfer function, why it is useful? So this is basically output current to output voltage transfer function. So this is nothing but this is Z. This is Z. Z is the output impedance. Output impedance. Okay. So for that we put perturbation in V2 V0, perturbation in D2 V0, and after putting these values, we get this transfer function. So this transfer function is also same as we have obtained from SSA. Now third one is very important because it is being used in a controller design. So this is V naught of S upon D of S. It means variation, how the variation of duty cycle affects the output voltage. That is studied in this. For that purpose, we put this IZ and D to be 0, perturbation to be 0. And if you substitute these values here, then we get this transfer function. After that, you substitute this Y naught equal to 1 plus SC, R plus RC, and this upon R into 1 plus SRC likewise. And this ZL. How does it come? So you can see here only, right? We defined it over there. Here, when we were defining this equation, then we had this variable ZL, and the ZL is nothing but this impedance. Similarly, when we were defining this equation KVL, then this is the Y naught. Y naught is nothing but the admittance of these two branches. So from here, this value is coming clear. Okay, so now after substituting this, we get this V naught upon D. This is also same as we had obtained V in state space averaging technique. Any doubts so far? Please ask me. So I give you 2-3 minutes. Post, please unmute the any participants who raise the hands or want to ask. Those who want to be unmute, please put your message in chat box that you want to speak. पूछिए क्वेश्चन पूछिए भाई.
Please raise your hand if you want to ask some questions.
कितने लोग प्रेजेंट है अभी? I'm not able to see.
Around 26 attendees.
Okay. Okay, so no question. Now let us see the effect of these non-idealities. What is the effect of these non-idealities on this modeling, and why we should be so much worried that we go into complexity, consider these things, then do all analysis, and does reality impact somewhat or not? So we'll try to see that. So these are the parameters we are considering. Let's say we are taking one modeling example where input voltage is 16 volt, output voltage is 12 volt. So what is the duty cycle? 12 upon 16. That comes out to be 0.75. Right? That is the duty cycle. Now load resistance is 11 ohm. Then inductance is 1.1 millihenry, but its resistance is there 0.18. Similarly, capacitor is there and its resistance is there. When switch is on, then it has this much around 44 milli ohm resistance. Similarly, when this diode is there on, then we have 24 milli ohm, and diode voltage drop is also there 0.7 volt. That is there. So by considering these non-idealities and by not considering these non-idealities, we will see. So it is sure that if I'm going to make an inductor of 1.1 millihenry, then wire will have certain resistance. But if I'm putting this value into simulation 1.1, then in simulation non require there is no need to have a resistance in series with that. But as I said that in practical case it is there, then what I need to do, I should consider it, right? I should consider it. So let's see if I put these values and try to find out the inductor current, output voltage, and duty cycle. So they comes out to be these three values. Okay. But if I put non-idealities and then calculate this value, so this is this one 1.05, 11.59, 0.75. Why it is happening so that output voltage is not 12 volt? The only reason is that there are a lot of drops in the output voltage. Not output voltage. There are a lot of drops in inductor, capacitor, switches, diodes, due to which your output voltage is not reaching to its desired value. And the previous classes we have seen that in order to meet that in open loop, you have to increase the duty cycle. So then only you will get the output voltage. Increasing duty cycle means you are extracting, more power from the source to meet those losses, right? So how does it impact on the modeling? So if you are putting these values, in those transfer functions which you have already obtained, then this is the non-ideal transfer function. This is a non-ideal transfer function. And if you are putting these non-ideal elements to be zero, you are putting these non-ideal elements to be zero, then what do you find? That this is a transfer function. Are you observing any difference in these two transfer functions? Anyone please let me know. Are you observing any difference in these two transfer functions? Extra zero, very nice. Extra zero. Yes. So we have extra zero. So now what is its physical impact that we will see? Now why this extra zero is coming? Due to this RC, right? Due to this RC. If we go back and see the transfer functions, these transfer functions. So this here, okay, we were at this transfer function. So here we are seeing that this is constant. This remaining term is constant. This is 1 plus S RC into C. So if RC is 0, then this 0 will not be there, right? So due to this RC only, this capacitor only, this extra 0 is coming into picture. And I will tell you this how we are getting these in MATLAB also. I will tell you that how to plot these results. So if I'm just observing the input voltage to output voltage transfer function, Then we have two plots. One is for ideal case, another is for non-ideal case. So this green one is for non-ideal, and this blue one is for ideal. So this is non-ideal and this is ideal. Similarly, this green one, this is ideal. Sorry, I wrote wrong. So this green is non-ideal, and this blue is ideal. What we see, if we do its analysis, the phase margin and its crossover frequencies, etc. Gain margin is infinite. What is this phase margin, gain margin? What is body plot in detail? We will discuss before the next class, before discussing the control system design. But for now, we know that for a system to be stable, its phase margin should be positive, its gain margin should be positive, right? And phase margin, if it is more, then system will have the less oscillations. And if its crossover frequency is more, then it will have less settling time. That much we need to know. Okay, so just I write here, gain margin should be positive, phase margin should be positive for a stable system. Okay, gain margin should be positive, phase margin should be positive for a stable system. And more phase margin, less will be the less overshoot. More phase margin, less overshoot, more crossover frequency. We will define gain crossover frequency and phase crossover frequency later on. So let's say gain crossover frequency, then your rise time or maybe settling time, or you can say speed of response will be fast. So that will be lesser. That is required, that we should have more phase margin, more gain crossover frequency. Gain margin also should be positive, it should be more only. But for DC to DC converter, gain margin is not a significant point. Okay, so what we are seeing here, that my actual system, non-ideal system, is having 55.4 degree phase margin. But this ideal system is having only 34 degree phase margin. It means my system, non-ideal system, is better. But because I neglected some of the non-idealities or all of the non-idealities, that's why the mathematical model which I have obtained is giving me information which is not accurate. Let us understand it later with further other examples. So this is, that V node perturbation upon I node perturbation transfer function. Here also we see the nature of transfer functions. We have this thing, we have minus of this. So here only 1 0 is there at s equal to 0. Here there are 2 zeros. So this transfer function is also giving different information. Why this negative is coming? Can anyone tell? This negative is coming here. I have not seen this in V naught upon Vg. Everything was positive, but here it is negative. आप में से कोई बता सकता है? क्यों ऐसा हो रहा है? Why this is negative? V naught upon Ij. The things are coming negative. So what does it interpreted that if there is variation, or you can say if there is increase in the IZ, then there will be decrease in the V node. Previous transfer function, what it was, yes, correct. So previously what was happening, if there is increase in the VG, output voltage will also increase. If it is decrease in the input voltage, output voltage will also decrease. But here, in this case, if there is increase in the IZ, then V node will be decreased. And that's true also, because we have taken this IZ to be like this, right? And this was our V node. So what does it represent? That if there is more load, if actual load is here only, and this is just perturbation. So let's say your 1 ampere is already flowing, and this is 10 ohm resistance, and this is total. You expect that 10 volts should be there. What happened now? You have put some perturbation of 0.1 ampere over here. So now the current which is being drawn from this is 10.1 ampere. So in order to meet this current, what will happen? Because power which is coming from input side, that is fixed at that particular moment. So in order to meet this demand, what it will do? This voltage will go down. So this change in voltage is like this was, let's say V1. Now it goes down and it becomes 9.9 volt. So this is V2. Now your I1 was 2.1. Sorry, I1 was 1 ampere only. Your I1 was 1 ampere, but I2 has becomes now 1.1 ampere, and we are trying to find V node upon I node. Right? So V node is V2 minus V1, so that is 9.9 upon 10, and this is 1.1 minus 1. I'm just it definitely there will be some dynamics in between. Just I'm giving a rough idea. So this value will be negative, upper value, this will be positive, and vice versa. If load is decreased, then this voltage will go up. Then this term will be negative, this term will be positive, this term will be negative. Right? It will be negative only. Okay. So you can see it's body plot and step response here. Also, we can here significantly see the difference. In this case, this is showing minus 20 dB, which shows that system is unstable, right? But it is 10.7, right? So next, let's say duty voltage transfer. In this case, you said that the difference is that this is having a zero, this is having no zero, constant is only there. So having zero is due to RC, present RC, right? Now, what is the impact of this? So let us do its body plot. So from body plot, we see that in ideal case, this phase margin is 4.85 degree only. And in non-ideal case, this phase margin is 26 degree, right? So what does it interpret? It shows that 4.85 degree is the available phase margin with my converter, but actually it is the 26 degree phase margin available with my converter. So if let's say I'm going to design a closed loop system and I need 50 degree phase margin of overall system after compensation and after controller design, then if I just see the transfer function given by the ideal analysis, then I have to arrange one controller which will give me 45 degree phase margin. I have to put all efforts to get this, to add this 45 degree. But in actual, I do not need 45 degree. I just need only 24 degree because my system is already having because my system is already having 26-degree phase margin. But how I will come to know? I will come to know when I do its non-ideal analysis, not with the ideal analysis. Okay. So this way it will help, right? This way it will help. And we will get accurate information. If we get accurate information, then we can get, maybe sometime we may need cheaper control solutions also. We need not to go for any advanced control. If things are already there with system, they just sometimes it happens. A few students are there. They just need to, you just give them hints or some little bit you guide them. They will do it their own. They need not to go for any coaching, or they self-study also. Just some motivation is there, they will do it on. But unnecessary, that student is intelligent enough and he can do, still we are putting him in coaching or somewhere. So what will happen? You cannot produce the more outputs. But if you know the characteristics of the system well, then accordingly we can design the controller. So that is the importance of these things. Now there are boost converter also, but boost converter almost it's time 30 minutes only. So boost converter modeling you can do your own just considering the same procedure. The only thing remains important in this boost converter is that when you derive the transfer function V node upon D, when you derive the transfer function V node upon D, then this transfer function V node upon D, if you derive, then you will have kind of nature is here like minus A1S plus or B1S plus V node upon S square plus A1S plus A node. This kind of transfer function you will get. And this type of transfer function, if you are getting, then this gives limitations on the controller design. We call it to be non-minimum phase system. Non-minimum phase system. Such systems we call to be non-minimum phase system. In such phase system, actually, the gain crossover frequency, this gain crossover frequency of the system that is very less, and it impacts the bandwidth. Control systems. Okay. So I thought that I will discuss this DC to DC converter also. So we will check in some another class if there is a time how to derive the transfer function for this DC to DC converter, because I wanted that one from second order, one from fourth order. So that we wanted, but anyhow we could not do it. So now let us focus on MATLAB part first. So this we will do later if time is there. Similarly, Jita server. I just tell you that final results, how does it impact this non-ideality? This is Jita converter, and you can consider all non-ideal elements here: RL1, RC1, RL2, RC2. These are the ESR of capacitors and inductors. Then this is the switch. This is the diode. By considering all these non-idealities, what we do, we get the different transfer functions. So we are considering here these non-ideal values in inductor, capacitor, everywhere we are considering. So for this, we derive the transfer function, and in both the case, ideal and non-ideal case. So you can see here we have 4 poles. Here also we have 4 poles. Number of poles does not change, but the value of poles, location of poles gets changed. right? Three zeros. There is no zero here, right? But here you can see S square. It means there are two zeros. There are two zeros. Two zeros. Okay. Two zeros already written. And these two zeros, where they exist in right half of S plane. One of them is in right half of S plane. So you must be knowing this right half or left half of S plane. So this one. So this is S plane. This is sigma, and this is j omega. So if your poles or zeros, whatever, if they exist in this part, this is called, this is S plane. So this is called right half of S plane, right half of S plane, and this is left half of S plane. So our pole should be, for a stable system, pole should be in left half, and also this zeros also should be in left half. But if zeros are on right half, then we cannot say that system will be unstable. But quite possible that if you make a closed loop, then system may become unstable. And also it will restrict the bandwidth of the system when this is in, because this will give this minus sign will create a problem. The location of all poles, if let's say this is G, then 1 plus G H you say, that is equal to 0. This is a closed loop characteristic equation as, let's say, 1 only. So this 1 plus G, when it goes 1 plus G, then these terms will be, added. These terms as Q, as square terms, this will be added with this. So if this term is more than this, then it will create a problem and it will give the unstable system. Okay. So this is its transfer function and its state response, and here also we can see that it is non-ideal system is giving good information. This is V naught upon I naught. In this case, 3 zeros, 4 zeros. So here also there are difference in the performance. This is the most important thing you see here in this V naught upon D, V naught upon D. So if you are using this V naught upon D, then what is happening? 4 poles. What is happening here? This you can see here, this one. This is S square minus some term, and this is S4. So S4 is okay. We will have 4 poles and they are in right half only. So this is negative sign. It means it is in right half. So system will be stable. But if you see there are 2 zeros and both zeros are in right half of S plane. The right half of S plane. Left half of S plane. So what we interpret from here? So we see that our original system is minimum phase. Original system is minimum phase. And if I go for non-ideal analysis, this gives me information that system is non-minimum phase system. So if I come to know that it is a non-minimum phase system, then I have to make preparation, or make preparation means I have to design controller in the same way. It's kind of thing that let's say some person is there, he's coming to us. Before he comes, if someone makes a negative impact of that, okay, that person is like that, like this, then what will happen? We have to be very much alert. We will talk him very sensibly. We will not talk anything loose to him. We will be very alert that we don't know what he may say. He is kind of, nonsense person. But in actual, he is the good person and someone has given you wrong information. So if he was the good person and he's coming to meet me, I will not be much disturbed. I will be cool, sitting in my office, doing my things, right? So knowing the system's dynamics, knowing the system's behavior as accurate as possible is very important. Otherwise, your controller design will affect, right? You have designed controller considering something else. Now your physical system, which is the real system, non-ideal system, demands something else. Then you may lead in different, different results, different responses which are not fitting. And you will say, okay, I have done good mathematical modeling, then I have designed proper controller, but it is not working with my hardware. It is not working with my system. So these things sometimes happens. It's not always that it's not required that for all systems only non-ideal behavior or the modeling will very much impact the control performance. No, but yeah, definitely if you know these things, then you can accurately design the things and you can perform better. Your system may perform better. Okay, so here also, as I said you that ideal system is that there is a right half plane. It means if I just close this system, make a closed loop, then my system is unstable. My system with unit gain, no controller system is unstable. But the non-ideal system analysis says that it's a 12.1 degree phase margin. That's a good, and this makes system to be stable. Okay, sorry. So we will see some of its MATLAB applications. Any doubt in theory, please ask. If you have any doubt in theory, please ask. You can be unmute. If you ask, then we will unmute you. So I'm just stopping to share this screen. This MATLAB screen visible?
Slide number 43.
No, just number. We cannot share multiple screens together. Okay. Okay. Now, are you able to see this MATLAB? Are you able to see MATLAB?
Yes, sir.
Only MATLAB window, na?
Window, yes, sir.
Okay, good. Okay, so now what we are going to do in next 20 minutes that we will see how okay, screen two.
I'm still working to learn more languages. I can't do that just yet.
So this slide is also visible. I think so.
Yes, sir.
Right? So what we learned today, just if I make it. Now I think both are there in parallel, correct? And both are visible, na? Slides and MATLAB both.
Yes, sir. Both.
Okay. So okay, fine. Now what we will see today in these things, that how to get this transfer function. So now let's take the non-ideal one only. I just remove all those things. So clear visibility. Let's do that. Okay, so for any converter, these matrices are with us. A1, A2, B1. Just transfer function we need. So we can do it through a program. So we will learn both the way. One through Leverrier, another through non without Leverrier. Okay. So what we do here, we consider that this IZ is 0. The DC value of IZ is 0. That is okay, fine. So these MATLAB basics of MATLAB I am not going to discuss. Just quite clear CLC or this format longy all does. So we have taken input voltage, we have taken resistance value, we have taken capacitance value, inductance value, duty cycle D. We have defined D1 just 1 minus D, RC, RL, RSW, RD, whatever value we have that we can define it, right? And there is one more term which is coming again and again, 1 upon R plus RC. That also I have defined as a RE for simplification, just simplification. Now I am writing A1 as it is in MATLAB. This A1 which is here, I am writing it as it is in the MATLAB. This expression I am writing over here. Okay. So this is minus 1 upon L R upon R plus RC. So that becomes RE, so it is minus R into RE upon L. Whenever you are typing in MATLAB, then you have to be very much careful that where is to be divide, where is to be multiply. That is very much required, right? Now A1 and A2 we have defined. Similarly, this V1, U1, V2, U2, V1, U2, V2, U2. What is that? V1, U1 is the matrix. Either you can write B directly, just you can put B also like this only, B1. But I have not put in that way. So this is 1 upon L 0, 1 upon L 0. And the second one is corresponding to second input U2. Similarly, this is B2 U1, this one, and B2 U2 is this one. Or you could directly write this is V1. I have again merged here. You see B1 equal to this B1 U1, B1. So this is kind of same thing, writing different thing. B1 you can directly write as it is, this and this, B1, B2. So C1, C2, we have C1, C2 also with us that we can put it here. So for simplification, it becomes just multiplication of all those R, RC into RE. So C1, C2 also we have put. Now again, we need to put E2. So E1, E2 in this case is not present. this, sorry, even is one. That everything over here also directly equal to 0 space minus this way also I could write it, but let's say I have done it in this way. So E1, E2 we can write J1, J2. So this is J1, 0, 0, J2 minus VF on L. Why it is coming? Because we are considering diode to be impact of diode to be in this model. So that we have put F1, F2, that is 0, we have put. Now, this is up to this we can easily, by analyzing the circuits, we can get the different system matrices, different matrices. Even if it is in 3 mode, 4 mode, so for every mode, we know the linear circuit and corresponding voltage and inductor voltage and inductor capacitor current we write, and we can do it. Okay. Now the issue is not up to this. This is simply based upon KVL, KCL. There is less likely to have any error. Now, the problem is how to calculate A and SI minus inverse. In that BD, calculating BD is a problem, ED is a problem, calculating X is a problem. Because X is equal to minus A inverse BU. So getting A inverse is problem, right? What we observe here that all these matrices are constants. Basically, they are a function of system parameters. So they are constants. Now, if they are constants, then it's very easy to write the matrix. If there is any variable, then there is an issue, right? So what we do now, we calculate the value of X. X is minus, so we define U first. What is the U? U is your VG, input voltage, and IZ. IZ is the DC value of load current, basically for perturbation. So DC value of IZ will be 0, right? Load variation, DC value of load variation is to be 0. So for X equal to minus A inverse VU plus J, this formula I have told you here. Here. Not this. So we deleted it. So we can see it here. In steady state, it is not written here, but you know that this formula is there, minus A inverse BU. So by writing that formula, what we X value, and similarly Y is CX plus EU plus F, that we can get. And this M is nothing but voltage gain. So we have calculated this DC value. After that, let's come back there only. Yeah, we need to calculate this BD. Now we need not to do it manually, right? We just write one instructions, this code one A1 minus A2, because that is with us. X we have already calculated X. This is simply matrix multiplication. This is not the element wise, so we will not use dot star, it is star only. Plus B1 minus B2 U plus J1 minus J2. So this we have written here. Similarly, ED formula we have written over here. Okay. Now, as I said you that this method which we are going to use for evaluating different transfer function, that is based upon state space way of transfer function evaluation. So in state space, a model is considered X dot equal to okay. Screen 2. I cannot write now. Okay, so you know that first equation is X dot equal to AX plus BU. Second equation, Y equal to CX plus DU. This complete two equations makes state space representation. And this command which we are going to use here to obtain the transfer function SS command, SS, that works on complete representation only. So the first thing is that when we are trying to evaluate the transfer function of state variable with respect to input variable, then we have only one equation. But if we are trying to evaluate the transfer function of output variable with respect to input variable, then we have y that will work. So in order to make the first equation complete, just x dot equal to x plus b, what we need to do? We need to introduce a dummy equation. You can say the y is basically x, y equal to x. So if you want to y equal to x, if you want to make it in matrix form, then y equal to c temporary x plus some d temporary x, where d temporary should be 0 and c temporary should be 1. So that's what we are doing here. E temporary, that is the unit matrix of size A. Similarly, E temporary is the zero matrix of size B according to this. So that we have considered. Now our system is having A system matrix, B new, then C temporary and E temporary. These things are with us. Now we can easily evaluate this transfer function with respect to input variables. So that is, hopefully I have these formulas over here. I'm discussing yes, this one. Yeah. So when we have this x, which is the state variable with respect to the unit, this voltage, output current, and duty cycle, 3 inputs. How many x? 2. X1, X2. X1 is IL, X2 is VC. So how many transfer function I should get? For this, 6 transfer functions I should get. So in order to complete this only, I have used this C temporary and E temporary. So we will write just one command. This is very important command. System1, which is equal to SS A, B, C, D. This is the format. A, B, C, D. So for us, A will remain A only. B is B new. C is C temporary and E is E temporary. So with the help of this, we will get these transfer functions TF SS1. So if I just run this much only, so we will give the selections. This is running. See, we get 6 transfer functions. Starting with, we get x equal to some value. So what is this x equal to some value? This is first is IL, second is VC or V node. So you can see it. Where is that? Yeah, this table. Yeah, this table you can see. This value 1.05 in case of non-ideal, 1.05 ampere. This is 1.15 into 10 raised to the power 0.59, 11.59 voltage we get. Why? Because in DC, V naught is equal to VC only, so this value are remaining same. Then we have various transfer function. First one is input 1 to output. So what is the input 1? V input. So this transfer function means V input into output, right? So for what is the first output, right? The output is inductor current. So this is IL upon V in, and this is VC upon V in. Input 2 is load current. So this is VC upon, VC upon IL upon IZ, and this is VC upon IZ. Third one is input 3 to output. What is input 3? Input 3 is duty cycle. So this is IL upon D, this is VC upon D, right? So these 6 transfer function we have obtained. Now after that, so up to this much we have run, right? Now what we need to do, we need to evaluate the output variable. So what is the output variable? V node only, that we need to evaluate with respect to input variable. With respect to input variable means V node upon Vg, V node upon Iz, V node upon D. All three we need to evaluate. So for that I defined again system 2. Now it was system 1, right, for which I was not having C and E, so temporarily I just considered unit matrix. But for this system I have A, B, I have CT also, and CT original CT. So that I will be using CT. I have used this term because C is basically used for capacitor. So whenever you are doing mathematical coding, please take care of these things. If I have used this C, let's say 84 microfarad here for capacitor, and again I am using this C for the CT matrix also here when I am evaluating this this C. If I put it C here, then what will happen? That capacitor variable now will be overwrite by this C, and it will be kind of vector. And whenever I need C in calculations, it will not be there. So some error will be there, right? So that we need to take care. Okay, so now I have defined the system 2, and system 2 I have defined. So just it makes the system state space ABCD form. Now for getting transfer function, I write this command tf sys2, right? So I could directly put also, then also it should work if I directly just for understanding purpose only I put it. Otherwise I could have written single command also, not an issue. Okay, so and what I do, so let me evaluate this. So if I evaluate this, then I have to remove this column. So if I evaluate this, then I am getting 3 transfer function further. So first one is V node upon Vg, second one is V node upon I node, third one is V node upon D. And you have seen these transfer functions over here, starting with this one. V node upon Vg. The first input is Vg. So input 1 to output transfer function. This is on your screen. 199.1 s plus 7.901 into e raised to power 6. So this transfer function is same as this transfer function over here, right? Now the second is your input 2 to output. So V node upon Iz. So input 2 is Iz. So if you see this, then this is the same transfer function as this one. This transfer function is same as this one. Okay, so that is also same. Now from input 2 to output, so that is V node upon D. Input 3 is duty cycle. So this is also same. This is also same. 4428 1.7. This. So this is V node upon D. But what we observe here that this is V node upon D, and if you see the previous one, this is V node upon C. Sorry, this transfer function is Vc upon G, Vc upon D, and you will see that the characteristics of both are different. What is the difference? Denominator remains same for all transfer functions. Numerator is different. Why numerator is different? Because this is Vc, which is the capacitor across, which is the voltage across pure capacitor. But this is V node. So now V node is not Vc. V node is Vc plus IC RC. So RC is coming into picture. Due to that RC, we have seen that a 0 is being introduced in this. Right? The 0 is being introduced in this. So that's why we can. That's how we can obtain the different transfer functions, and then we can analyze them. And if you see here, okay, then we can, let's say this third one only we analyze. So I just run this. So if I run this, then V naught. Okay, I need to run this one. Let's see this zoom. So this figure 3. This figure 3. So this figure 3 is now my body diagram. It's giving me 26-degree margin, which I have shown here. 26-degree margin at this is 18 per second. I think edit access to page. Okay, so we can change it from here. This is the access property. Even in radian per second, we can do it. It is 9. Actually. Just one see. Okay, now if let's say I make these things to be 0. If I make these things to be 0 and just comment this and run the entire program, let's say again, then you will see this is the ideal transfer function. And if I am able to see figure 3 again, yeah, this is the figure 3. So in this figure 3, you can see that now for ideal case, this is 4.85 degree only, which we have shown here, 4.85 degree only. It's in radian per second, it's in kilohertz, that's why this is not matching. But yeah, it's system. You can see it one at so this is 26 degree. Another you can see one more, let's say this one, this is 4.85. So you can like that observe anyone at a time. No one, no. Okay, so we can easily do the analysis that what is the the system and what is the original availability with the system, how much you need from controller. So that is that can be done, right? So there are other ways also how to get the transfer function, how to use this Lavoisier algorithm, that we will see in next class. So any questions you may ask, please. If you have any query, please ask. So if no query, we stop over here. We'll meet tomorrow with some new speakers. So thank you very much. We stop over. Please unmute. Okay, Ravi. Please unmute this Mr. Ravindra Kolu. EICT host, please unmute him.
Yes, sir.
Okay, what are the main reason for the non-ideal nature? So main reason is losses only, there is losses in the non-ideal inductor. So that we represented with that. Similarly, in capacitor also there are losses. Switch also there are losses. So to represent losses, we consider these resistance in series with the particular component. हाँ रविंद्र जी बताइए.
Hello, sir.
Yes, Ravindra ji, please tell me.
So in slide number 43,
43, yes,
can
40.
you just
But I have to share. I think it's not visible to you now, right? So,
listen.
yes, 43 is there now.
43. Yeah. What is the significance of this GM negative and PM negative? I mean, how? Yeah. Sir, am I audible?
Yes, again,
Yeah. Both the GM and PM are negative. It means that the system is unstable.
yes.
Ideal case, yeah. Or
Yes.
even non-ideal case also PM is negative, but it's a open loop. I mean, it's just a converter.
No, so what
Just-
this actually we will discuss in control, but because you asked now, what is this response? Let's say we have a simple converter, right? So whatever this transfer function is that for the open loop converter, right?
Yes, sir.
Now this body plot, when let's say I represent it to be GS equal to whatever transfer function we have with us, right? Now what I'm considering, this transfer function has some property, some less gain margin, whatever it is there. Now I'm
Yes,
just simply making it closed loop with unity feedback.
Okay. Let's
With no
assuming that the
compensation.
sensor feed, gain is 1. Something like
Yes, sir. So this is sensor gain is 1. So this is 1 plus GS.
Yes.
Now what these body plots are basically, what are the body plots? They are based upon the GS information, but
Yes.
this is the representation of closed loop of GS,
Yes.
right? This is
Yes,
giving
and-
information.
From this we can ascertain the closed loop stability. I got that.
Yes,
But,
sir. So this is giving stability of GS upon 1 plus GS.
Yes. And but what what I didn't get is this is the transfer function output voltage to output current. I think E naught by
Yeah.
I
V
naught or IZ.
Yes. So
If it is unstable, what does it physically? What does it mean?
So physically, it means that it means variation in the input voltage. What we expect if there are like load, it's increasing the voltage should decrease, and after some time it should get settled. Perturbation should be in limit, right? But it does mean
Okay.
if there are so much perturbation that even after if load is varying, then output voltage perturbations are not stabilizing.
Okay.
Right, so it cannot handle that. If
Okay.
same thing is in made in that, for to ensure that we have to some computer design, controller design, then this problem will not be there.
That is for the
Then
P case, right, sir? Output voltage, load current to output voltage.
Yes, 3 cases. So, but for controller design, we don't use this first two.
Of course.
Controller design either V naught upon D or maybe IL upon D also we use if we are going for current control.
Yes. Current control. But then what is the use of that V naught by IZ?
Analysis purpose. That how much variation could be there, how much rejection is there, disturbance rejection.
Okay.
But,
Property we have.
this also I will try to cover in control system. But how dynamics will vary if I'm varying the input voltage and how much variation will be there in the output voltage. Change in input voltage, change in output voltage, simply change in load current, change on output voltage. So after compensation also, if it is not proper,
Okay.
it means our system will not take care of particular input variation or load variation. So normally people do not check because with vnode upon d itself, they think that the system is stable now, but we should check it.
Okay, sir. Okay. Right, sir. Thank you.
Okay, thank you, sir. Any other query, please? So we stop over here. Thank you. Thank you for patience listening. Thank you.
Thank you so much, sir, for telling us about modeling of ideal as well as non-ideal DC to DC buck converter using state space analysis through theory and as well as through lab session. Thank you so much, sir.
There is one query about these session materials. So I think some of materials which we have obtained already that are uploaded in here in Canvas.
Sir, whatever we have.
So not very, Ramesh sir, writing method. So I will make use of this and will say to you. Means on obviously. So it will be available. At least you can ensure by 10th of July, because once we complete this, then we will ask all speakers. Then as soon as we get, we will upload it, and you can access it anytime. Your query is valid. Thank you. Okay, fine. Have a nice day ahead. Thank you.
Thank you, sir.